What's up, chem nerds? Welcome to another episode of your boy Mapoy's chemistry videos. Today we're going to go over organic chemistry. So we'll start with what is organic chemistry, and we're pretty much dealing with all compounds that include carbon. That's what it means to be an organic compound. You include the element carbon. Some other main points about organic compounds is that the bigger the compound, the higher the boiling point. Most of them are generally non-polar or weakly polar, which means they can't dissolve in water because water is a polar molecule. It's also a non-electrolyte simply because it can't dissolve into ions in water. So when you put an organic compound, mix it in with water, it doesn't mix well and it can't dissolve into ions. So that's why it's a non-electrolyte. Another important fact about carbon that I forgot to mention is that carbon has 4 valence electrons, therefore they can only hold 4 bonds each. And we'll start with the most basic type of organic compounds, and these are the hydrocarbons. They're composed of carbons and hydrogens. And there are 3 types: alkanes, alkenes, and alkynes, and each of these are broken down based on the type of bonds included in each of them. And we'll start with alkanes. So here's some facts about alkanes. They all contain single bonds between the carbons, and it's considered saturated because of the single bonds. And here's the general formula for alkanes: CnH2n plus 2. So as an example of that, to show an alkane, so we have 3 carbons, that's our N. So if we double that 3, we get 6, and then you add 2 for a total of 8. So based on the general formula, we should see 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Next we move on to alkenes, which have 1 double bond between carbons. Because of that double bond, it's unsaturated, and its general formula is CnH2n. So however many carbons you have, you double the amount to get the number of hydrogens. As our example, let's do C3H6, and I'll show you. We have 1, 2, 3. Let's put a double bond here. Now be careful because carbon can only hold 4 bonds. This middle carbon already has 3 bonds, so we only add 1 more hydrogen. And this carbon at the end has 2 bonds, so we have to add 2 more. 1, 2. And let's count. 1, 2, 3, 4, 5, 6. There we go. And then lastly, we have alkynes, which have 1 triple bond between the carbons. And it's also, like alkenes, unsaturated because of the triple bond. So if you have a double or a triple bond, it's considered unsaturated. And its general formula you can find on table Q, CnH2n minus 2. So you double the amount of carbons to get and subtract 2 to get the number of hydrogens. As our example, C3H4, you double 3, you get 6, and you take away 2 to get 4. So to show what this looks like, let me do it in a different color. So let's do 1. Alright, then you gotta add hydrogens. Now notice here, this triple bond counts as 3 bonds, so this carbon can only hold 1 more hydrogen. This one, 1, 2, 3, and 4 doesn't need any more hydrogens, and then this one could take 4 hydrogens. So we count 1, 2, 3, 4. That's it. And those are our 3 basic hydrocarbons. This you could find table Q of the reference table. Now when it comes to naming these, you gotta look up the prefix, suffix, and the numbers. This you need table P for. So the number of carbons in the main chain tell you pretty much the prefix. And you have to look up table P as an example. Meth equals 1, eth equals 2, prop equals 3, so on and so forth. You have to look at table P for these prefixes. The suffix tells you type of organic compound, basically. whether it's an alkane, alkene, alkyne, or even some of those that include the functional groups. So you kind of need to use both table Q and table R for those. And the number, it indicates for location for the bond, substituent, or functional group. As an example, let's look at an alkene, C3H6. So we draw with 3 carbons, 1, 2, 3. We know it's an alkene based on the general formula, so you place a double bond. Or actually, let's, right here. And then you draw the rest of those things. Now, because there are 3 carbons, you have to look it up on table P, what the prefix is. It's prop. Now, because it's an alkene, we're going to take that ending, propene, and then we have to indicate the number to show where is the double bond. So we got to put a number 1 because it's right after the first carbon. Now, let's say you have an even longer chain. Let me pull up another slide. Now let's say we have this, 4 carbons. Put a double bond here. Okay. So because there are 4 carbons, you should look up the prefix. It's but for 4 carbons. It's also an alkene because of the double bond. And because of that, its name will be butene. But we got to figure out where's the number, and we got to count after which carbon it's placed. 1, 2, 3, 4. So it's after the first one. So it's 1-butene. What happens if we change the location right here? Now we just changed around the double bond, so this is still a butene. But we gotta figure out what's the number now. 1, 2, 3, so it's after the third carbon. However, you could also count from right to left. So it's still going from right to left, it's after the first carbon. Typically they go with the side where it's smallest. Ideally, would you rather prefer a 1-butene or 3-butene? For our IUPAC naming system, they go with the smallest number, the smallest denominator, you could say. So it's still considered 1-butene because going from right to left, it's after the first carbon. You could consider either left to right or right to left. Now we get into this thing called substituents. And these are things in which you substitute a hydrogen in the hydrocarbon with. Typically, they're halogens or alkyl groups at its most basic level. So for every substituent you add, you have 1 less hydrogen. So do not follow the general formulas when trying to write a formula for them or drawing their structures. So halogens, these are the group 17 elements. Examples include chlorine, bromine, iodine, etc. What else is there? Fluorine. Forgot about that one. Okay, alkyl groups. Those include methyl, ethyl, and etc. It's kind of like another hydrocarbon chain, as an example. So I'll draw a few of them for you. So here, naming system goes the same way as you would for double or triple bonds. You have to name the carbon in which the substituent is added to. So this one has a fluorine attached to the first carbon, so it's 1-fluoropropane. Fluoro, you need to add those sort of prefixes again. Alkyl groups, same thing, you gotta put a number next to the carbon in which it's attached to. So methyl group kind of look like this. So it looks like a whole other hydrocarbon chain attached to the side, kind of. That's what it looks like for alkyl group as a substituent. Then we get into isomers. They're basically the same molecular formula, same atom composition, different structure and arrangement. That's the only thing that's different, is the way you arrange these atoms. It's the same formula, same atoms. You just structure it differently. And because of this different arrangement, it leads to different properties. And the more complex this organic compound is, the more isomers, the more possible isomers there are. So as an example, let's try this. Basic so far. A sure way of pretty much making an isomer is attaching, well, I guess the most basic way you could do it is taking one of these at the end and attach it as a substituent in the middle. That's my surefire way of making an isomer for a simple hydrocarbon. So notice what I'm going to do here. Look at this right now. You went from basically butane, rearrange the atoms again to make 2-methyl propane. Not only do you arrange the structure, you rearrange things, you also change the name. But again, we're going to make sure we have the same atomic structure, same atomic composition, as well as molecular formula. So just to make sure, we have 4 H's here, C4, H10. And we got to make sure that it matches up on the other side as well. So we have 4 carbons, 1, 2, 3, 4, and 10 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see the same thing over here. 1, 2, 3, 4 carbons and 10 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. So you rearrange these atoms, you should still end up with the same number of atoms. Same molecular formula, you just structure it differently and you get different name as well. So please understand that these isomers not only have different arrangements, they have different names and different properties. Okay, now table R will be your best friend for this section on functional groups. So different functional groups leads to different properties. So alcohols have a single bonded OH group, while you'll have also some other things like aldehydes and ketones with double bonded oxygens, whether or not it's placed at the end or in the middle. You have to make sure you know some differences. Ketones have double bonded O in the middle, aldehydes have double bonded O at the end. These are different kinds of functional groups, which then leads to different properties. Different functional groups lead to different properties. You also have nitrogen as another possible functional group, which makes it amines, or its placement can make it amides, and you might have amino acids. Again, different properties. So what you're going to definitely need to do is identify what's different in your organic compound. You're not going to have your basic hydrocarbon chain. Identify what's different, and then match it up with what's on the reference table. And then you're going to have certain processes, certain organic reactions that lead to the formation of these organic compounds with certain functional groups. As an example, alcohols and esters. Okay, and then we go into the 7 organic reactions we covered in class. So here we'll start with some 3 that kind of similar in a way. So for substitution, you're basically substituting a hydrogen for a substituent. Typically a halogen substituent. As an example, a halogen, like fluorine, bromine, iodine, etc. Addition is where you break up a double bond or a triple bond, typically a double bond. So you could allow these carbons to take on more hydrogens. Polymerization, you're basically combining monomers to become polymers. So these monomers have to be of the same kind. So you're probably adding a bunch of monomers like glucose to make a higher level like cellulose. Combine multiple monomers to make a polymer. Okay, and I'll show you a little bit of what these reactions look like. So substitution. Okay, so we start with this. Combining with a diatomic halogen to yield this. So you take away some hydrogens. Well, for this case, we're taking one away to put an F there. And where does that F go? I mean, where does that spare hydrogen goes? It goes with that lone fluorine, and they make an acid together, like hydrofluoric acid. For addition, so let's say you had something like this. Now here, if you want to have these carbons take on more hydrogens, you need to break up this double bond. Oh no. So once you break that up, you bring in more hydrogens, make it a single bond between them, and then now they're able to hold more hydrogens like that. Now we go on to some of these other ones. The most important thing you need to know about these 4 reactions is what's required for them or what it makes. Okay, so combustion, usually take an organic compound because carbon's a necessary component to this, plus oxygen to yield CO2 and water. Okay. So combustion, think of starting a fire. That's an example of a combustion reaction. Things you need to remember are these things. You need oxygen, and CO2 and water are products. Fermentation creates alcohol. From sugars especially. Esterification makes an ester. And saponification makes soap. So for these reactions, fermentation, esterification, and saponification, you need to make sure you know what each of these makes an alcohol, makes an ester, and makes soap. For alcohol and ester, for fermentation and esterification, you probably need to be able to identify that you're looking at an alcohol or an ester. So that means identifying the functional group and matching it up with table R. So you need table R to help you in case they give you structures. So remember that fermentation makes an alcohol, esterification makes an ester, and saponification makes soap. And that brings us here to the end of this video, where basically the reference table will be your best friend for this organic chemistry quiz. You need to use table P for prefixes, table Q for knowing alkanes, alkenes, and alkynes, and using table R for functional groups. So you'll always need to identify what's different in the compound and then match it with the table. All right. Good luck, guys.